I'm going to start by looking at permutation. Now, a permutation is an arrangement of a number of objects in a certain order, where each permutation is the actual arrangement. So next I'm going to look at how to calculate the total number of arrangements. Okay, so what's important for permutations is that each arrangement has to be in a certain order. I'm going to start with something that's really common to all of us, something like bike locks. We originally called these combination locks. Really they should be called permutation locks because the order of the arrangement actually matters in a bike lock. So we need to get the right code in the right order, which is a permutation. So let's say you've got a bike lock, you've got a 4-digit code. These are the positions that I have available to me. So I write out boxes for each position. So in the first position, we're allowed to use the numbers 0 through to 9. And in this case, for example, we're allowed to use the number on more than one occasion. So if there's 0 to 9, that's 10 numbers. So in the first position here, I've got 10 options to choose from, 0 through to 9. In the second position, because there is repetition allowed, I also have 10 options. 10 options again in the third, and 10 options again in the fourth. So in this case, I've got 10 options for my first, second, third, and fourth. So when I want to work out the total number of arrangements possible, so that is going to be 10 by 10 by 10 by 10, which is 10 to the power of 4, which is 10,000. So I've got 10,000 different arrangements there possible. So if you're trying to crack that code, there would be 10,000 different arrangements. So it would be pretty hard to try and crack it if you didn't know it. Now what we're going to do is we're going to see what happens when we don't allow repetition. So if a code is used in the first position, it can't be used in the following positions. So when we don't allow repetition, in the first position we're still choosing numbers 0 through 9. So therefore, in the first position, we're allowed 10 different options. But if we've used one of those numbers in the first position, we're not allowed to use it again. So actually in the second position, we're only allowed 9 options. Then in the third, we can't use either of the first 2, so we've 8 options. And in the fourth, we can't use any of the first 3, so we've only got 7 options. So to work out the total number of arrangements there, we just multiply those numbers. So that is going to be 10 by 9 by 8 by 7. Which is equal to 5,040 different arrangements. So you can see when we start eliminating choices, the number of different arrangements goes down dramatically. We've gone down by nearly half, okay, from 10,000 to 5,000. So we've effectively taken a code and we've said, right, you can use 10 different numbers, but we're taking 4 of those numbers at a time. And now that's going to be important for a little bit. Let's just say we had a 10-digit code without repetition. How many different arrangements could you have? Well, if you had a 10-digit code, then in the first position you'd have 10 options. In the second position you'd have 9 without repetition, then 8, then 7, then 6, then 5, then 4, then 3, then 2, then 1. So that gives you a total of 3,628,800 different arrangements. So to try and crack that code is going to be obviously very difficult if you've got a 10-digit code without repetition. Now, just to go through a bit of notation, you can see here that we're successively declining 10 by 1 and multiplying it by the next number every time. There's a term for that in math. The term is called the factorial function. So that number is essentially just equal to 10 factorial, denoted by an exclamation mark. That's on the calculator as well. So it's just if you press 10 and then shift on the top right, x to the power minus 1, you've got 10 factorial, which gives you that number. So 3,628,800. A lot of codes there, okay? So I've introduced factorial. It means it's just to multiply a series of descending natural numbers. Now, let's get back to the 4-digit code here without repetition. And I want to look at and introduce factorial, because essentially what I've got here is a situation where I've got a choice of 10 numbers and we're trying to arrange them a certain number of ways, just taking 4 of them at a time because it's a 4-digit code. Okay, so this comes into questions all the time where you're taking a certain number of objects, but taking a few of them at a time, or taking a certain number. So what we say is we're taking n objects or at a time. So when we want to calculate the number of arrangements of n objects taking or at a time, there's a formula and an easier way to do it. So the formula here becomes n factorial over n minus or factorial. So if I go back to my pie clock, I'm taking 10 objects, which are my 10 numbers, so that's 10 factorial, divided by 10 minus 4, because I'm taking 4 of them at a time for a 4-digit code, which is 10 factorial over 6 factorial, which gives me 5040. We can think of this another way. So I can just show you how we get to the original calculation from that. When I've got 10 factorial, that's 10 multiplied by each successive number in descending order until I get to 1. So that will be this number divided by this number, because that's 6 factorial. And hopefully you can see there that the denominator just cancels into the numerator, or divides in evenly to the numerator here, and we're just left with the calculation that I had at the start, which is 10 by 9 by 8 by 7, which is my 5040. So that's really useful when you're calculating the number of arrangements of n objects taking or at a time. There's even an easier way on the calculator, and that is np or, which is a button on the calculator. So what we press here is, I'm just looking at a Casio FX 85GT Plus calculator. 10 shift multiplied by a button to give me 10p or, and the or is going to be 4. So we're going to press 10p4, and that gives me my 5040 different arrangements. Okay, so this is how we calculate it. Just that button on the calculator for permutations. Just look at another question now. If I had 9 letters, let's say, and I wanted to count the number of arrangements possible just taking 3 letters at a time. Well, I could start by my first method. If there's a total of 9 letters, then in the first position I have 9 choices, in the second position I have 8 choices, and in the third I have 7 choices. That gives me a figure of 504. In the calculator, if I've got 9p3, because I'm taking 3 at a time, which is 504 when you're calculating. And what I'm going to do is bring that into something called a combination next. Now the only difference between that and a combination is, let's say 3 of my letters were A, or, and T. Well, in a permutation, A or T would be a different arrangement to T, A, or, because the order matters in a permutation. But in a combination, the only difference is that that will be the same. So, looking at a combination is the arrangement of objects where the order does not matter. So effectively, when I'm dealing with a combination, those two are the same. So when calculating out, if that was one arrangement, and that's a different arrangement, in a combination actually it's the same. So if you're looking for the total number of combinations of 9 letters taking 3 at a time, rather than the permutations, in our calculation we have to take out the number of arrangements where these are the same. Okay, and the number of arrangements where these are the same is going to be, well, there's 3 by 2 by 1, which is 6. So that's 3 factorial. So we have to take that out of our calculation when we're dealing with combinations. So in our calculation, what we're going to do is take out the number of times that the 3 letters can be arranged in different ways, because we're not bothered about that in a combination. So in a combination, we're seeing how many times can we make an arrangement of objects where the order doesn't matter. So if I've got 9 letters taking 3 at a time, then I'm going to have the same calculation at the start, my 9 factorial, which is n factorial, over my n minus or factorial, because I'm only taking 3 of the letters at a time, I'm not using all 9, and what I importantly need to do is take out my or factorial. And my or factorial was 3. because 3 factorial is the total number of ways that the 3 letters can be arranged differently, and in a combination we're not interested in that. So the total number of combinations I have there is 9 factorial over 3 factorial times 6 factorial, which is 84. Another way of doing that on the calculator is simply to go to the calculator, press 9, then press Shift Divide, which is the NCOR button, and press 3. So it's 9 objects taking 3 at a time. That gives us a number of 84. So there's 84 arrangements where the order doesn't matter. There's 504 arrangements where the order does matter. So let's say you were to make a football team or something like that. Out of a total of 11 players, you needed to make a 5-a-side team. How many different arrangements could you make? Because in a football team, if you're taking 5 players out of 11, we don't really care about what order we take them in. We're just seeing how many different ways can I take 5 of those players out of the 11. So if we were choosing 5 players from a total of 11, we've a total choice of 11. We're taking 5 from that. So in total there'd be 462 different combinations. So that's a summary of what I've done in the video. We've looked at permutations, we've looked at combinations, and the fundamental principle of counting. In the next video, I'll probably look at some past paper style questions on this topic.